The projector. It's yeah, if you go and see yourself, yeah, oh, I don't know if you remember so. Oh. Okay. Once we start to our security by on, like slides or plans. They're black, like black slide. So like. If you are, I'm what's being more? Okay. Ready? Think so. Yeah. Yeah. No, no, no. No, like that. Then you write some like you get more. Even help. That's very well. I don't my phone. We have to do enough. Feel it to me. I was thinking about my. I tried my. No, I don't. But maybe it's not going to be done. Welcome to our chemistry magic show or colorful chemistry. So we are the SKS chapter of American Chemical Society. I'm the president, Connor, and then I'm going to just pass the microphone down and let everyone else introduce themselves.
My name is Camden. I'm a surveyor. Fortunately.
I'm Erin. I'm a PhD student that got roped into this. Instead of studying, I'm here. And I see my high school science teacher here. Hi.
My name is Will Powell. I also got roped in this 10 months ago. I was working on my exam. And I'm also a master's student.
I'm Carmen. I'm the vice president of ACS and I'm a senior.
I'm Hannah. I do public relations for ACS and I'm a junior.
I'm Sierra. I'm the secretary of ACS and I'm a senior.
I'm Alex, and I'm a president.
I'm Pascal, I'm here to help out.
I'm Isabella. I am a junior.
Alright, so tonight we have a bunch of experiments laid out for you guys, and some of them are kind of tricky to kind of imitate magic, but all of them have to do with chemistry. So our first one is going to be done by Hannah, and let her take it here.
Okay. Alright, so we're gonna start here with 4, just regular cups. 50 milliliters of water here, I'm gonna put into one of them. And now you have to watch, and I'm gonna mix them around and you tell me which one has the water.
Watch carefully, don't lose it.
Alright, you think the water's in this one? Do you think the water's in this one? Definitely no. What about this one? No. Okay. What about this one?
Oh.
Alright, so what happened was we had a polymer in there called polyacrylate. And he's gonna show you. So what happened is we started with the polyacrylate is a monomer. And what happens when you put the water in it is it sort of turns into a polymer and it is like a bunch of molecules all strung together into one thing. And that's kind of what this is showing. And so like this one right here is kind of like what you use in diapers. So it's very absorbent and then it all sticks together. So if you have a diaper, you don't want stuff leaking out of them. So that's all this one is.
So our next experiment is gonna be done by Sierra and him. And Beck.
Okay, I'm back. So we're just gonna put a bunch of water in these beakers right here. Hard to see. And what we're gonna do after we're done putting in water is a phenolphthalein test, which is a pH test. And if you don't know what pH is, it's just sort of the measure of acids and bases. So an acid would be something like lemon juice. It's kind of like sour when you taste it, it might make your mouth feel kind of bad. And then a base would be like sodium bicarbonate, which is baking soda. I don't know if you've seen your parents bake cookies or something like that, they might put baking soda in it. And other bases would be like soap. You wash your hands and it kind of gets all the dirt and grime off your hands. So now, when you put an indicator in it, it's gonna change color and it'll tell you if it's an acid or a base or where it is on the spectrum, and that's what you see here. Acids are sort of orange and yellow, and the bases turn blue up here. We're gonna see what this color turns into when she puts the indicator in it. Alright, and nothing happened to that. So what does that mean? It means that it's right in the middle here. You've got water in there. Here's another one, she's mixing it together. Alright, so that one is just the regular phenolphthalein. That's how you know that it's working. That's how you have the indicators in it. So what do you think is gonna happen to this one? Do you think it's gonna be an acid or do you think it's gonna be a base? That's it? Right, nothing happened to that. So it's a bit more neutral like water again. One more, acid or base? pretty light, so it's probably more of an acid over here. This whole one.
Alright. Well, I think right now, do you guys have any questions? Yeah? So. In movies, you'll see acid like melting through metal and stuff. There are some acids that can do that, but it's not gonna react that fast. So. What we had for this one was vinegar, which is just everyday household item, and you can put it in food and stuff, and it's. Let's see, I think vinegar's around 4 or 5, if I remember correctly, which is pretty. It's like, it's not that bad for when it comes to acids. You come way down here, you get like battery acid, which is gonna burn your skin if you touch it, and that can start growing things. Depends on what you do to it. So by itself, there's a few strong acids. They're like hydrochloric acid or sulfuric acid, like the ones that come to mind right away that are like really strong. And if you have them by themselves, they're going to be down in this range. If you have like vinegar, they're going to be up here. So there's, think about 5 strong acids. I don't remember the number exactly, but then there's a lot of weak acids. So the strong acids are like right here by themselves, and then the weak acids are around here. Then there's also strong bases and strong or weak bases, which the strong bases would be here. So like sodium hydroxide, which is used as a drain cleaner sometimes, will be down here. And cancel will be around 10, or baking soda, which another everyday high in the household is 8 to 9. What's that? If you get it on your skin, yes. Alright, so we're gonna move on to our next experiment, which is the chemical traffic light. If our presenters for that would like to come out.
All right, hello, everybody. And as Connor mentioned, we're going to be doing an experiment called the chemical traffic light. Now, this experiment has to do with a phenomenon in chemistry called oxidation and reduction. And I'm not going to get too much into it because it's a topic that even confuses high school and college chemistry students sometimes. But the main idea is that reduction is the gain of electrons and oxidation is lost. And when a chemical goes through this process, you can see several changes in its appearance, for example, and that's what we utilize here using color. So I have a solution of what's called indigo carmine. It's a dye. It's a dark blue color, as I hope everybody can see. And Carmen here is going to add it to a solution of potassium hydroxide and sugar. So basically basic sugar water. And when she adds it, we can see the color went from that dark blue to a nice green. Now, you probably remember this is called the chemical traffic light. So if we let this sit just for a while, if you can see now, it went from that green color to a nice dark red. And eventually, with enough waiting, you can see it lightening up. So green to dark red to lighter red, and slowly but surely, we're going more into like a red orange, and soon, pretty much a yellow. I think I can call that good enough. Yeah, but Carmen, if you would like to cap that Erlenmeyer, the cool part about this reaction is it can happen in a cycle. It's reversible. So. Would you like to shake it up? So when you shake up the solution, it reacts with the oxygen within the flask, causing the chemical that was reduced to reoxidize, and then it goes back from yellow to red to green. And if we let it sit for a while, it'll go back down to red to yellow. And that's the chemical traffic light. And we can take a few questions if anybody has any. Yes? Same thing they use in lava lamps? No, I don't think so. Lava lamps have to do with a phenomenon called density and polarity. That's a whole nother purview. Yes. Yes. Why do we have on goggles? Because any chemical you work with either in the lab or here does have the potential to be dangerous if you got it in your eyes. Yeah, that's the main thing. You just don't want anything in your eyes. Like even water can get unpleasant in your eyes, right? This one does not explode, but I'm pretty sure we do have a few things that will explode back into the ships. Yes. Sorry. How did it turn green? Okay, so when we shook it up, there is a lot of oxygen left in that flask. So when you shake it up, it allows all the indigo carmine to interact, bounce around, and react with that oxygen, which then oxidizes it, bringing it back to the green color. All right, I'll do one more question. Yeah. Oh, are we gonna do the marking done? I don't think it's on the docket for this one, sorry. All right. And if there, yeah, okay, one more question? For the most part, it's only those colors, starting with the blue, and then the green, the red, and yellow. You could adjust it a bit with how much dye you put in there to make the colors lighter or darker. But yeah, this experiment, as far as we know, as far as we are able, it's just those 4 colors. All right, thank you guys very much.
So, who's heard of elephant toothpaste? That is our. So, who knows how elephant toothpaste works? Raise hands if you know how it works. Alright, so. Does anyone know what hydrogen peroxide is? Household item, normally 3% in your medicine cabinet. We have 30%. So we have a lot more of it in the same area of space. So hydrogen peroxide, when you just let it sit there, it will decompose and it will turn into water and oxygen. And so it just does that very slowly, and throughout the day it would do that, or it just slowly decays. Now, if you were to add a catalyst, which who knows what a catalyst is? Yep. So a catalyst is basically just something that speeds up the reaction in various different ways. So when you add a catalyst to this, it takes it from happening in days to a matter of seconds. Which, if we do it right, we might get a little messy. Oh. Alright. What color should we make it? Start throwing them out. Some blue. Some green. So we're gonna do 3 colors in 3 spots, so it hopefully will be a line color on the side of it. We got blue, green, and yellow. Alright. See how well Phil can do at this. So the catalyst we are using is potassium iodide. And so if you can tell, it's bringing a lot more of the green or yellow color. So the iodide itself, when it reacts to this, it looks like yellow. And so we have a green, and the blue and yellow are just working together also to make more green. So it's a yellowish green right now. But anyone have any questions? Go over here. So, when you mix the potassium iodide and the hydrogen peroxide, it decomposes into the water and oxygen. And the oxygen is gas, so it takes up a lot more space than a liquid does. And we added soap to catch the bubbles so you can see it. That's why, look, if we didn't add the soap, it would just be a little bit of bubbles and you wouldn't see much rise up. Back. No, that will not be our only explosion. There'll be a better one. Right up front. No, it cannot be used for rush element speed. So hydrogen peroxide, normally you don't want to consume it. It's not the best thing for your body to consume. It's toxic to you. So you can wipe your teeth with it, but it's better not to consume it. We'll do one more question for this. Can you say that again? Not active. You can't use, so a catalyst just speeds up a reaction between a few chemicals. So like this one, it's just one chemical being sped up. If you were to wanting to make a tree grow faster, you just give it the nutrients it needs. That's like you eat a lot, that helps you grow. You give the tree food and it will grow faster. So we'll move on to our next experiment. So our next one is involving fire. So
Okay, while the lights are getting turned down, who here likes fireworks? Okay, unfortunately, we're not allowed to light fireworks off indoors, it's a safety hazard. But instead, we're gonna show you some of the chemistry behind fireworks. So, have you guys ever wondered what makes fireworks a certain color? Like why this firework's red, and why another one's blue, and another one's green? So it's all based off the chemistry. And so the reason why some fireworks are green and others are blue, let me go back, is based off of the elements located within the fire. So who here knows what an atom is? Good, most of you. So we all know that an atom is made up of 3 main particles, right? You have a proton and a neutron, which are located kind of in the center. It's called the nucleus. And you have a bunch of smaller particles called the electrons that are kind of zooming around the center, right? And so these particles, these electrons, can absorb energy So like when you add heat to something or you light it on fire, for example, and then once they kind of release that energy, they can emit a photon or light. So that's kind of what's happening, which is why when you burn something, sometimes they glow, right? Make sense? Okay, so we're gonna give you some examples of what different elements kind of look like when they burn, and so every single element has a very distinct electromagnetic spectrum, which is kind of a big fancy word for saying the different colors of light that it emits. And it's all based off of how much energy these electrons absorb and they release. So, okay, what's our first element? All right, so our first element is copper. What color do you think it's gonna be? Just shout it out. All right, who's ready? You guys got to see the green flame? All right, so when you guys see a green firework now, and you know there's copper, right? There'll be a quiz afterwards. All right, so now up next we have calcium. What color do you think it's gonna be? Red? Okay, it's kind of a nice red orange color. All right, what up? We're gonna just. All right, next up we have lithium. What color do you think it's gonna be? It's like pink red. All right, up next we have potassium. What color do you think it's gonna be? Kind of a nice like light purple color. Okay, we got one left. We have lead. What color do you think lead's gonna be? All right, that's our flame experiment. All right, do you have any questions? We will for our next experiment. We'll have to turn it back on eventually. Okay, you there in the blue? How does the different colors work? So the different colors are based off of the electrons that are kind of zooming around the atom, and it's based on how fast the electrons are going. When they like speed up, they'll gain energy, and then when they slow back down, they'll release energy. And they release that energy in light that we can see, and based off of how fast they slow down, it depends on the color. Does that make sense? Okay. You back here on the page. Because we didn't have an element on hand that burned. Yep. What was that? What does diamond's color make? That's a great question. I don't quite know. Diamonds are made of carbon. And I would assume it'd be pretty similar to like burning wood, because wood also has a lot of carbon, so it'd probably be like a nice yellow color, nice reddish yellow. Over here, in the white. How can we do what? Make lighter colors? Like brighter or like lighter colors? It's a great question. I don't quite know. You can't really change the like intensity of the light based off of the elements you burn. I think it's just kind of how much you're burning, if that kind of makes sense. The more you burn, the brighter it's gonna be. Okay, you in the front, last question. So we had little sticks of wood that were soaked in a solution with different elements. And then when we stuck that stick of wood that had our chemicals on them, they burned different colors. All right, now for our next experiment, we'll be doing fluorescence.
Alright, so with the flames and all the different elements we were doing, what was that called? Emission. So for in chemistry, there's different ways you can get light. There's emission, which we had just shown you and demonstrated, where it absorbs energy in a certain way and then it will release a photon of light. There is also fluorescence, which generally best used with black light, which is ultraviolet light. And so if you can see my nice white lab coat looks blue. We also got our fun, colorful sign. If I can grab it properly. So, who thinks they know what's happening with this? Down up in front. So this is ultraviolet light, which is it's also called black light. So you got the visible spectrum, which goes from purple to red. Past the purple is ultraviolet. Past the red is infrared. Infrared is just like heat, mostly. The ultraviolet, you can get it from the sun, or we can make nice lamps that do it. If you've ever been to an like arcade or skating rink or something, they'll have black lights a lot. Who, I saw a hand over here. You think you know what's going on with fluorescence? So it is making it glow. So making it glow. What, anyone else have any other part of what's happening? I can't see, I think there's a hand over here. So what's happening with fluorescence is similar to the emission. It's not absorbing it and then emitting it. It's emitting it's making it emit its own light. So this, you can kind of see a blue. You can see all the different colors on that. What else then has special inks or something that change color under black light that will fluoresce? I'll give you a hint. It's for security reasons. So like on driver's license, you can see, so in my hand, we got a South Dakota driver's license. You can see a bunch more things on the driver's license. State of South Dakota's in there. It says South Dakota across it. The year it was made, it's got some stars. And then we also got an Iowa license, which has Iowa on it. The year was also so 1846 and 1889. So. The reason they do this is it makes it a lot harder to counterfeit license and make fake ones. So if you just take a black light, you can see if it's real, because it will have all the fancy markers. Any questions right now? And I can't see anything. Alright. Yes. Yes. So. It depends, so it's basically just depends on what molecule or element, so molecule being just a couple different elements put together. So it depends on what element is there and it will glow in a different manner. Or it won't glow. Any other questions right here? So there's a. So in order to make white, generally things are bleached, and the bleach itself often will have the bluish glow from the fluorescence. So black lights will fluoresce in blue on white below them. So like if you use a black light and you can, like in a crime scene, if you see like on cop shows and stuff, is that what you're asking? So partly, so what they're using is called blue melt. They'll spray it on there, and then they'll be able to see bodily fluids, so like blood, urine stuff from that. Because the blue melt will attach to the blood that was there, even if it was cleaned up with bleach, and they'll be able to see it now. So there's a special chemical that they add, and it just sticks to stuff that was there, and it helps indicate. Okay. For the black light? So it depends on what molecule it is, so like bleach or blue malt will glow like that blue, nice blue color. There's certain dyes or certain molecules in here, but you'll be able to see like they'll glow a lot better of whatever color these are. It depends on the molecule basically to answer your question. So it depends on what it is. So like if it's water, it's not going to do anything, but if it's tonic water, it will glow blue as well. It depends on what it is. We'll do one more question. Alright. Any more questions right now? In the back?
How do dry bubbles turn into like really cold stuff?
So the dry ice bubbles, it's our next experiment. And we'll have some people explaining what's going on with that. Nope. Guys like.
So, just, you all know what dry ice is, right? We've all used it, yeah, but it's a molecule, it's a gas, normally, breathe it out. It's not oxygen. Carbon dioxide, right? So carbon dioxide, the formula is CO2, there's one carbon atom attached to oxygen atoms. And so here we have dry ice, and then it's actually really, really cold. So in South Dakota, we get pretty cold, like maybe -40 in the last week or so. But with this stuff, it gets to -78 degrees Celsius. or -109 degrees Fahrenheit. So that's really, really cold. So my friend Alex here, I have him wearing something called cryo gloves. So cryo means frost or icy cold. So this is just gonna protect his hands from handling it. And this stuff you can actually buy yourself. So in Halloween parties, I'll make it extra cool, get it comfortable. Put some of this stuff in there. It won't leave a weird taste in it. It'll make some real nice things. And we're actually gonna see that. So I will put the beaker in here. It's just gonna contain the mess that we made. And then just as a comparison, we're gonna put the dry ice in this beaker of water just by itself. And so I'll have you grab some dry ice. And if you do this, you have to have your parents with you. You have to promise me, okay? This stuff really hurts if it gets on your skin. Actually see what it is. Put like a bunch of chunks. This one. So you can see this vapor on top. Who knows what that is? Well, I guess. It is really cold air. So the dry ice is actually really, really cold. And so in chemistry, sometimes we would need an ice bath. So that's just frozen ice, frozen water, but we don't want the liquid there. So if we don't want our stuff to get contaminated, but we need to keep it really cold, we use dry ice because when it goes through a process called sublimation, it goes straight from a solid to gas. It's called sublimation. Then we skip the liquid phase, and then our nice process won't get contaminated by any liquids that we don't want. And so if we add some soap bubbles, and then we'll see another cool phenomenon with the soap bubbles, and then once we put that on. So Alex, very kind of to put soap bubbles in there. If we squish it, all that water vapor comes out. And this is actually safe to touch, but the ice itself is not. This is okay for you to touch. The water is also okay for you to touch, just not the ice itself. You're trying to be very, very safe. No, you don't know. Who thinks they know how dry ice is made? It's a really cool process actually. So carbon dioxide normally is a gas, right? So we exhale it, it comes from burning stuff, it comes from other chemical processes. So what companies actually do, they have generally a mixture of gases, nitrogen, oxygen, carbon dioxide, maybe some argon in there. They actually have these special equipment that can actually separate all of those gases out. So first step, you take out all the oxygen. Second step, take out all the nitrogen. Third step, then you just left with this carbon dioxide, and then they squeeze it really, really tight. They apply a huge amount of pressure, and they cool it down. Then they can get it from the gas phase down to a liquid, and then back down to the solid that we have right here. And so, yeah, that's all I have. If there's any questions, you can try to answer them. Yes, dry ice can actually burn your hand. So you would think that burning your hand or burning your skin comes from touching something hot, and that's also true. But it's just the drastic change in temperature that your skin experiences is called the burning sensation. So if I were to touch this dry ice with my bare hands, it would sting really bad, and it would actually cause the first layer of my skin to kind of burn and cause it. So that's why if you use this, you should have like some tongs. Yeah, tongs, or if you have if you want, you can buy these special gloves to handle the emergency imperative. See a man who's waiting patiently. How many Kelvin? You know what Kelvin is? Yeah. Wow. So I can actually calculate that real quick. So Kelvin, we have several units of temperature. We have Fahrenheit, we have degrees Celsius, and we also have Kelvin. Then Kelvin is a much more scientific way, so in the community, 194 Kelvin. How we do that, we just take the Celsius degree number, and then we just add 273 points to that. So -1, -78 plus 273 gives us 194. Was, why does the dry ice make vapor when it's in the water and not when it's in the vent? Alex, if you can pull out some chunks and just hold it in your hand and fit. So you can kind of see it if you go on it. Yeah, if you let it, yeah, so you can see some vapor. It's just you can't really see it in the box because it's hidden. But the soap, what the soap bubbles did is that it allows some detergent in there, and then as the gas escapes, the gas goes into the bubbles, and you can see a visual representation of the gas coming out. And also you can see that with the grayish, smoky vapor as well.
Right. Now for my favorite one. What do you think I have in this doer? Okay. I will give you a hint. It's liquid. Liquid nitrogen. So, lower the temperature of the dry ice. -79 Celsius or about -110 Fahrenheit. So I'm just gonna average it to 110 Fahrenheit, okay? What do you think the temp of liquid nitrogen is? One's a solid, one's a liquid. Throw out numbers. All right, I got 250. Anyone think they can get closer than 250? -250. I'll give you a hint, you need to get lower. All right, so the temperature of liquid nitrogen is -320 degrees Fahrenheit. So that's a lot colder, a little under 3 times colder than the dry ice, but it's still a liquid. So what do you think you can do with something that cold? You can take a racquetball, bounce it, right? Do you like to step or hit the racquetball? Bounces. What about the racquetball that's been in here for the entire show? What's gonna happen in that? No. It's shattered. So why does it do that? It got cold. So we'll start this. You take a racquetball and it bounces. Why does it bounce? So it's elastic. It's like a rubber band. It can, you deform it and then it shoots back and it gives a little more energy and it will be able to bounce. When you freeze it, you remove any flexibility to it. So you can shatter it. What about a flour? Take a flour and stick it in the liquid nitrogen. One, it makes it boil. Two, when you take it and hit it against the table, what happens? So, same thing happened. You're freezing it, and it's no longer flexible or elastic. It can't move, it doesn't have enough movement between the bonds to protect itself from that. So, if I take my hand and I hit it on the table, my hand's fine, right? The flour was not fine after liquid nitrogen. What happens if I stick my hand in the liquid nitrogen? So I take my hand, I stick it in the liquid nitrogen, but I can still hit it. My hand's fine. Why can I go and stick my hand in the liquid nitrogen? Why can I touch the liquid nitrogen? If I would stick it in there and I would leave it in there, it would freeze. Yes. Why does it not freeze right away? We'll go back there.
Then.
So, as he had said, that is exactly it. Your hand is warmer than the liquid nitrogen. What's your body temperature? 98. That's 98 Fahrenheit. The temperature of this was what? Negative 320. So that's almost 400 degrees difference. So when you stick your hand in there, you get a little air bubble. And the air bubble protects you from the nitrogen until the temperature difference goes away and then it starts freezing. This is called the Lake Frost effect. What else can we do with nitrogen? I'll also say this. What else can you do with difference in temperature of airs? So, yeah. So warm air rises, like a balloon. I can't say the first name, but Charles Law, if you've ever heard of Charles Law, basically saying when you heat up air, it becomes less dense, and less dense things go up, right? So what were to happen if I had Carmen stick a balloon in there? It would deflate. How many balloons do you think she could get in there? 2? So it's gonna pop, it's gonna deflate. Any other option? It's gonna freeze. Alright, 3 options. Pop, deflate, or freeze. Let's see which one's right. So that's one balloon. Let's see how many more she can get. 2 balloons. 3. When should she stop pushing them in? Never? We'll let her decide when she wants to stop. So, what were the 3 options? Deflate, freeze, and pop. Did you hear anything pop? Alright, so that one's out. So deflate and freeze. Which one do we think's happening? Deflate? So you saw the balloon, right? What did it look like? So it deflated. Why did it deflate? Air got cold. So the same thing happens in opposite. If you take air and heat it up, it expands, it takes up more space, becomes less dense. If you make it cold, it shrinks and takes up a lot less space. What is liquid nitrogen? Just nitrogen that's cold, right? What's our atmosphere made up of? Mostly nitrogen, and then oxygen, and a bunch of other random gases. So we have our liquid nitrogen, which is much colder than the air, and it's obviously liquid. We take the balloon, put it in there. What do you think is happening on the inside of the balloon?
Air is losing, and it's taking up much.
So there is the same amount of matter inside of the balloon. It's getting colder. So when you get colder for air, it gets smaller in size, it condenses. And once you get cold enough, it'll turn into a liquid, like the liquid nitrogen, or you have to look really closely, but if you were to be able to see inside the balloons, you would be able to see liquid. So the air is being being condensed into a liquid. Now what happens when she takes them out? Well, expand. So just like that, the balloons are back to their normal size. Why are they becoming big again? The air is expanding because they're warming up. So when we had the balloons and nitrogen, the air inside the balloon became liquid as well. What would happen if we take the liquid nitrogen and heated that up really fast? It would expand. It would shrink. What would happen if we put boiling water in that tube over there? Oh, we got water. So Phil is going to fill up that tube with near boiling water. And then if we take this and fill it in there, what happens? I'm not going to answer it, but I'll let you guys see. All right, so all right, if you guys can all stay at the edges of this row or farther, that would be great. Please don't sit in front of the can. That's called the can. Okay. So we'll throw nitrogen. All right, can I get a countdown? 10. So what happened? Have an answer on what happened? Well. So we took the liquid nitrogen and expanded it back to a gas, really fast. Alright, you guys wanna see it again? Alright, they're gonna refill the nitrogen, so just give us 1 second. Okay. We got near boiling water in the tube. And that's, what temperature is boiling water? 212 Fahrenheit. Alright, so another countdown. Alright, so what happened with that again? You're fine, so we take liquid nitrogen and heat it up from 300 negative 320 Fahrenheit to 212 degrees Fahrenheit. And it turns back to a gas really fast. Alright. Do we have any questions? That's no. Alright, any other questions? Not this time. Alright. So. One thing that we always do at the end of our shows, we have flowers left over. So pull up. Come up here. So, come on. So, every organization on campus has a faculty advisor. Ours is Philipova, and she helps us out immensely. So every show we give her the extra flowers. So. That is all we have, so unless there's questions, thank you for coming. And. Don't play with my connection by yourself.